Jai Hind to everyone. Today I'm going to discuss topic that I have taken from material science. Subject code is BOE 303 and the topic is plastic deformation. So it is very critical topic. If you are going to understand this topic properly, means you can easily understand the all phenomena that happens due to this plastic deformation. So if you go through the syllabus, here you can see this mechanical property. Under this first topic is tensile test, plastic deformation and all. So I have chosen this topic for this lecture. After that, you can easily understand this dislocation due to slip and twinning, as well as what is strain hardening concept. So these topics can be easily understood by you. So let's start this thing. Why we are going with this plastic deformation? Because if any component is undergo with some load, here in this figure A, if you see, we are applying tensile load here in opposite direction. Because of that, the original length of workpiece is changing and it will remain constant if it undergoes under plastic deformation. If you come to this, here we are applying compressive load, opposite direction. So here, if the compressive load is going to apply, the original dimension you can see here L0 will change to L. So similarly, there are so many other methods with the help of that we can apply different forces. Like here we are applying shearing force, like this, suppose one part is there, we are trying to like apply opposite direction forces on the top and bottom surface. One more force you can apply by twisting. Suppose some cylinder is there, you can just apply twist rod. So because of that also there is some change. So when any object going into permanent deformation, that is basically called as plastic deformation. So going to the next slide, for like how we can prove this plastic deformation experimentally. For that we have to perform some test. One of the test is tensile test. Under that we have to first understand the basic structure, or you can say basic design of tensile test specimen. So here I am just doing hatching of this specimen so that it can be highlighted here. So this red one is our tensile test specimen. So by using this you can easily like check the all properties of this material. So here if you see, this is overall length, then this distance matters a lot, that is here showing this gauge length. So it is very important while we are doing this tensile test. And here you can say dia or width of this. So width is right term for this. So this is standard width, and we have to observe the change that is going to happen in this area, so that we can conclude whether it is going under plastic deformation or not. So after getting this specimen, you can go through this kind of machine, where standard like machine that comes is UTM, Universal Testing Machine. In that you can perform tensile test as well as compressive test. So these two tests we can perform here. So suppose I am going for first apply this tensile test experiment. So I have to fix the same specimen that we have seen in before this figure. So like this. So here I am going to clamp this with this machine, and here this portion I am going to clamp in this machine. If you see, this is the like actual picture that you can observe here, and through these two jaw we are trying to pull this component, or we are trying to stress this. So here, as we discussed, this is something that is known as gauge length. So here we are trying to observe what kind of change is going to happen here. So that can be easily observed by some with this machine. Normally some computer is there, on that you can easily see the readings. What kind of reading we have to see, that you can see here. If you plot any stress strain diagram, so this is basically for ductile material. So ductile material stress and strain diagram, if you see, on x-axis we have strain, on y-axis we have stress. So here it goes like this. So there are like few points that you have to observe during tensile test. So these are the few points. Like first is goes straight and ends at A. So what is A point here? A is basically elastic limit or proportional limit, where this material can revert back to their original shape. But beyond this, if material crosses this limit after A, so in this area, if it going, so this point is known as yield point. And also this is again, if you see here, one is upper yield point. So this is upper yield point. And one is lower yield point, LYP. Normally we denote through LYP. And if we are keep applying load, it crosses again this limit and goes like this and reaches up to D. So D point is basically a very important point, that is ultimate tensile strength. So ultimate tensile strength, you can see we are getting this much. So if you are going to, if you see this ultimate tensile strength, if you draw horizontal line, so it is the maximum strength that your material is going to bear. So this is ultimate tensile strength, and after that, if you are still keep applying load, means it will get fracture here, means the workpiece get broken. How this can be observed on this stress strain diagram? So here I have given one figure, in that you can see if you are going to relate this, like if this region we are going to observe, that is elastic region or elastic deformation, where material can be revert back into their original shape. So here you have to come through this diagram. So this was the original. Here you can say this relates this. Beyond this elastic deformation region, this plastic strain or plastic region start, and this plastic regions divided into two groups. If you can understand, if you are remembering, this point is ultimate tensile strength. So up to this and after this straight line. So this region is known as uniform plastic deformation, and here you can say this is non-uniform plastic deformation. So these are the like two plastic regions that we are getting here, and after that this fracture is going to happen. So we have observed, if material is undergoing under this elastic deformation, we are going to get almost same specimen that we have used for test. But beyond this, if we are going to pull our specimen, now it is entering in uniform plastic deformation. So we are going to get some increase in length. So this length basically is going to increase as compared to, like from top it is same, but from bottom you can say elongation started here. So suppose this is L1, that we are getting more here. Then after this region, you are going to enter in non-uniform deformation region. So this is suppose L0 length. Here we are going to get L1. Here we are going to get L2. So this is the change in length, L2. And after this, here some more elongation will happen for very fraction of second, and it will get fracture. So for this reason, we are getting suppose L3. So this is L3. So here we can easily say L naught is less than L1 is less than L2 and L2 is less than L3. So here continuously we can say length is increasing here because of constant load that we are applying here. So this is the actual phenomena. If you can relate both tensile test specimen with respect to your stress strain diagram, so you can easily understand the four critical regions. You can easily understand what is four critical regions. First one is elastic deformation region. Second is this uniform plastic and non-uniform plastic. Then last one is fracture region. So you can easily relate all these three things. In this slide, again, I'm trying to give you more like insight of this stress strain diagram. So as we discussed here, it is our elastic region. And after that, this B point, you can say, start of the entering of the yield region. So after that, upper yield point, lower yield point, then ultimate tensile strength, then fracture. So if we are keep trying, if we are like pulling our component, see here, why this strain hardening region is written here, that you have to understand. Strain hardening means if you are again and again pulling and releasing any component. If I am going to stress this component and after some time before fracture I am going to release this, then again pulling, then again release, pulling, release, means it will produce a kind of hardening on the material. So that is known as strain hardening. So that regions here, suppose any material having certain strength, I want to increase this strength. By what phenomena I can increase? I just pull this thing, I just apply this some load and release that load, then again applying load, then again releasing of load. If this thing I am doing again and again, so you will see a little bit strength of that particular component got increased due to this effect. So we have clearly understand up to this, we have elastic region where material can get into their original shape, and here this is plastic region. So whatever deformation is going to happen in plastic region, that is known as plastic deformation. And here you can easily relate in the terms of atoms here. Suppose if you see any atom structure, suppose on microscope, this is my specimen, I am going to observe their microstructures or these atoms. So you will see up to this region, this elastic region, my material is going to behave like this, means very little shift in, some deviation is there, very small deviation is there, and that can be easily achieve their original position while we are removing load here. If we are going to remove load here, then it will come into their original shape. So you will see it is like covering all the surface. So it will be in uniform pattern. So like that. But if I'm going beyond this, as I said already, up to this, our material can come back into original shape. But after crossing this limit, if I'm going to enter in this, means some elastic plus some plastic combination here, it is going on. So how our material will behave? You can say there is some plane. Against that, our atoms are shifting. So these are known as slip planes. Based on that, it is shifting and it cannot be like going back into their original shape. So these are the things that you have to always remember. When stress removed, plastic deformation remains there. So this is the key that you have to always remember. When stress is going to remove, this plastic deformation remains there. So some terms you must understand, like what is the ductility, meaning what is the resilience, toughness and hardness with respect to your this stress strain diagram. And one more thing I want to cover here, as I said, we have discussed ductile material stress and strain diagram so far, but if you are trying to draw brittle material stress and strain diagram, it will almost come like this blue line. Here we will go up to elastic region, then little mix of elastic plus plastic. After that, it get fracture. It is kind of you can understand in this way. Suppose I am having one mild steel plate. So this is suppose mild steel plate. Mild steel is a ductile material. And ductility is basically that can be drawn into a wire. If you are going to apply force, first it will draw some wire, it will reduce their dia, it will increase in length like that, then it will get fracture. But if I am having same plate, if I am having one more plate, but that is cast iron. Cast iron is basically a brittle material. So if you are going to apply force after very little amount of like stress, it will get fracture. Suppose from this height, suppose from 4 feet height or 4-5 feet height, I am going to drop my cast iron plate, it will broken into 4-5 pieces. But similar experiment if I am going to perform on mild steel, it will remain in single piece. So this is the basic difference. That's why here fracture is going to happen very early stage. So that's why if anybody asks draw stress strain diagram for brittle material, you cannot draw the same. You have to draw this up to this limit. Means proper elastic region, then little bit mix of plastic plus elastic region. Means you can say where yield point starts up to there, mainly this brittle material got fracture. So if we are talking about some definition, what is ductility? As I already discussed, ductility is a property in which any material can be drawn into a wire and material experiences very little or no plastic region. But if now if you discuss this resilience is the property of any materials to absorb any when it is deformed elastically, then upon loading to have this energy recovered. In similar way, toughness means energy absorbed under stress strain diagram. Suppose this is stress strain diagram for ductile material. So energy absorbed, the area under stress strain diagram is basically shows the toughness, the property that is indicative of materials resistance to fractures when a crack is present. So before fracture, whatever energy it is going to absorb, that is known as toughness, and hardness is a property that basically defines the resistance to localized plastic deformations. Means suppose I have to check the hardness of this particular suppose plate. What I have to do, I have to find out more harder material and we have to apply some load. So some small penetration based on our needle, based on our ball shape, indenter, based on indenter structure, like it may be diamond type, it will project, it will do some localized plastic deformation, and later on we have to just measure the depth of penetration and other parameter, what area it is basically deforming under load, so that we can check. So hardness is again a very important property while we are defining this plastic deformation and other things. So up to this we can easily like differentiate between elastic deformation and plastic deformation. Let me repeat again. A temporary shape changes into a self-recovery reversing after the force is removed, so that object returns to its original shape, and that is called elastic deformation, where this shape can be retracted again. But In the plastic deformation side, if you see, plastic deformation is the property that offers any material for permanent deformation. So here you can say change in shape upon load removal. Here change in shape upon load, no change in shape you are going to get upon load removal. After like removing of this load, if there is some change, that means we are having this plastic deformation. If after removal of my load, if I am not getting any change in shape, that means elastic deformation. So these two things you have to properly understand and apply at each and every place, so that you can easily understand the concept of this plastic deformation. And it happens basically due to two types of mechanism. One is slipping and one is twinning. So just if you just see this slipping versus twinning case, in this diagram you can easily see, suppose I am observing this atom and their positions here. Because of this slip plane, this structure got disturbed. Like here we have 1, 2, 3, 4, 5 atoms, but here in some row we are missing. Here we have 4, then 3, then again 5. In between that, some mismatch is there, and these are the known as our slip planes. Because of slip planes, so this is slip direction. Because of that, some deformation happened and it is permanent. While we are doing comparison with twinning means here in twinning you can say everywhere the numbers of atom in row is same, but it got twisted, somehow it got twisted only. So this is the main difference between difference between slip and twinning, and both are basic thing that we have to follow under plastic deformation. So here we refers to slip as the prominent mechanism of deformation of material. So these two things you have to understand before applying any plastic deformation. Maybe you are following slipping mechanism or you are following twinning. So there are some difference that you can undergo, but main thing I have declared, like because of some twisting effect or some, if the row atom wise is same, then it may be considered as twinning. If somewhere we are finding some atoms are missing at certain row, that means it is a case of slipping. And one major difference you can see, it occurs in several milliseconds, but here it occurs in few microseconds. So this is again one good difference that you can understand. So these are the few questions that can be asked with this topic. What is plastic deformation? State two difference between plastic and this slipping and twinning thing. Then what causes plastic deformation? Is plastic deformation is reversible? Like that, several questions comes from this topic. So this is all from this topic. Like I have covered plastic deformation. Before that, how we can observe this plastic deformation through experiment. For that we have to perform tensile test. And how we can perform tensile test specimen, we have discussed about their specimen and how each stages of stress strain diagram we can relate with this tensile test specimen, so that this plastic and elastic regions can be differentiated. So and after that how many mechanism are available for this plastic deformation? You can say slip and twinning is the two mechanism through that we can undergo this plastic deformation. So you have to understand this concept before concluding this plastic deformation topic. So thank you everyone and Jai Hind.